Welcome everyone to the Tutte Colloquium today. We have speaking from the University of British Columbia, Stefan Willigenburg, on the 3+1 free conjecture of chromatic symmetric functions. Whenever you're ready.
Thank you very much, Logan, and thank you all for coming today on a Friday afternoon, and thank you very much to the organizers for inviting me. It's an honor to be able to speak to you today. So just before I get started, one thing that I would like to do is just check that everybody can hear me. So give me a thumbs up, either using the reaction button or put your physical thumb up if you've got your camera on. And that's wonderful. Okay. And again, if for some reason my sound goes out or the slides aren't moving on at any point, please just feel free to unmute yourself and just holler and I'll fix it. If you want to ask questions, again, feel free to unmute yourself and ask or pop it in the chat. Logan, I would ask for your help there. If a question comes up in the chat, if you could let me know, please, because my slides are here talking to you folks and the chat is over on my second screen, so I can't see it if I'm looking at you. So would you be willing to do that, Logan?
Yes, that sounds good.
Wonderful. Thank you very much. So then, without further ado, what I'm going to do is I am going to tell you about the 3+1 free conjecture of chromatic symmetric functions. And if you don't know what any of those words mean, then don't worry. What we're going to do is we are going to introduce all of the characters that we need for the talk over the next 45 or 50 minutes, and then have a look at some of the recent results in the area and also some conjectures. I know we have a lot of graph theory fans here, so maybe something will whet your appetite. So, okay, without further ado, except, you know, apparently my button isn't working. Let's try this. Yes, okay, thank you. So we're going to start off a little earlier than the chromatic symmetric function. We're going to start with the chromatic polynomial. And so this dates back to BIRKHOFF in 1912 when he was trying to solve the four-color theorem. And for the chromatic polynomial, what we need is the notion of a proper coloring. So what you're going to do is you're going to color the vertices of your graph in 1 up to k colors, such that if two vertices are joined by an edge, then they've got to be different colors. So for example, this thing right here is not a proper coloring because you've got two vertices joined by an edge and they're the same color. However, here we have two vertices joined by an edge, which are different colors. So this is a proper coloring. And then with this in mind, the chromatic polynomial is then the number of proper colorings with k colors of your vertices. So if we take this graph right here and we have k colors, well, for this first vertex here, we've got a choice of k colors to color it with. Then with this one, we only have k-1 colors left to color it with. And then with this one right here, we've only got k-2 colors left to color it with. So the chromatic polynomial, therefore, is going to be the product of these, so k times k-1 times k-2. Now, this heuristic works occasionally, but it can let you down. However, the one thing that will never let you down is deletion-contraction when you're computing your chromatic polynomial. So let's have a look at what it means to delete and contract. So if you have a graph G, then you just remove an edge to get G delete E. And if you want to contract, well, then what you're going to do is you're going to shrink an edge, shrink, and then identify the vertices to get G contract E. And then Birkhoff's deletion-contraction theorem was that the chromatic polynomial of G minus that of G delete E plus that of G contract E is equal to 0. So now with that in mind, what we're going to do is we're going to bring things a lot further forward in time, and we're going to look at the chromatic symmetric function. And this was introduced by Richard Stanley at MIT in 1995. And so for this, what we're going to need is we're going to need the concept of a proper coloring again. However, now instead of having only K colors, instead what we're going to have is we're going to have infinitely many colors. But again, we're going to have the same concept that we had last time, that if two vertices are joined by an edge, they've got to be different colors. And then, given a proper coloring of the vertices, we're going to associate a monomial in commuting variables with that coloring. And what we're going to do is we're just going to have X, the color on vertex 1, X, the color on vertex 2, and so on. So for example, if cyan is color 1, magenta is color 2, and lime is color 3, then this coloring right here is going to give us the monomial x1, x2. This coloring right here is going to give us the monomial x2, x1, but remember our variables commute, so that's the same as x1, x2. And then this coloring right here is going to give us x1, x3. Okay, so with this in mind, we can now define the chromatic symmetric function. So given a graph, its chromatic symmetric function is, well, what you're going to do is you're going to take all proper colorings of that graph, you're going to make the monomial associated with those colorings, and then you're going to add them all up. So let's have a look at an example. So say we take this graph right here, and yet again, we're going to have that cyan is color 1, magenta is color 2, and lime is color 3. So then this coloring right here is going to lead us to x1 squared. This coloring right here is going to give us x2 squared, and this coloring right here is going to give us x3 squared. Then this coloring right here is going to give us x1, x2. This coloring right here is going to give us x2, x1. And as we saw on the previous slide, that's the same as x1, x2, thusly giving us the term 2x1, x2. Similarly, these two colorings right here are going to give us 2x2, x3, and these two colorings right here are going to give us 2x1, x3. So that's the chromatic symmetric function, and it's going to be the focus of the rest of the talk. So before we move on, do we have any questions? Just feel free to put it in the chat or just unmute yourself. No, everyone is looking good. In that case, then let's move on. So now, instead of deletion-contraction, for the chromatic symmetric function, we're going to have multi-deletion. And this started with Rosa Oriana and her student Jeff Scott back in 2014. And they came up with triple deletion. So say you have a graph such that you have three edges, E1, E2, E3, forming a triangle. Then the chromatic symmetric function of G minus that of G delete E1 minus that of G delete E2 plus that of G delete E1 and E2 is equal to 0. And you can actually extend this from a triangle to an actual K cycle. So in this case, what you need to do is you need to take K edges forming a cycle. And then what you're going to do is you're going to fix this last edge EK. And you're going to do absolutely nothing with it. You're not going to touch it. And then what you're going to do is you're going to take a subset of the edges E1 up to EK minus 1. And then what you're going to do is you're going to make the chromatic symmetric function of the graph G minus that subset of edges along with an appropriate sign. And then when you add all those things up, you're going to get 0. And so multi-deletion is what we can do for the chromatic symmetric function. You're not going to get a classic deletion-contraction, because notice that when you contract and two vertices become one, you're going to have a drop in degree. And so therefore, that's not going to work out with your monomials. It's not going to work out for the chromatic symmetric function. However, if you make a beautiful change of going from just regular graphs to graphs with weighted vertices, then you actually do get back a deletion-contraction rule. And if you want to know more about that, well, you are working with the world experts on this, because this was developed by your very own Logan Crew and Sophie Sperkel. So if you want to know more about that, then ask them. Now, I've kept saying that the chromatic symmetric function is a symmetric function, so we should really justify that name. So what does it mean to be a symmetric function? Well, a symmetric function is simply a formal power series in commuting variables such that, well, if you have your function and then you permute the variables, you get your original function back. And so therefore, our chromatic symmetric function truly is a symmetric function, because notice that if you have a proper coloring and you permute the colors, then you get another proper coloring back. So our chromatic symmetric function sits inside what's known as the algebra of symmetric functions. So what we're going to do next is we're going to have a look at the algebra of symmetric functions and some of its classic bases. And we're also going to then look at how you can express the chromatic symmetric function in those classical symmetric functions. So let's have a look at our first basis, which is going to be that of power sum symmetric functions. So what we're going to need to do first is we're going to need to have the indexing set for our algebra of symmetric functions. And this is going to be all the partitions. So what's a partition? Well, a partition of n is going to be a list of positive integers, lambda 1 greater than or equal to lambda 2 greater than or equal to lambda 3, and so on, whose sum is n. So for example, if I take 3, 2, 2, 1, then this is a perfectly nice partition of 8, since 3 plus 2 plus 2 plus 1 is 8. And so with this in mind, we can now define the ith power sum symmetric function. So this function pi is simply going to be x1 to the I plus x2 to the I plus x3 to the I, and so on. And then given a partition lambda, then the power sum symmetric function p lambda is simply p lambda 1 times p lambda 2, and so on. So let's do an example. Say I wanted to compute p21. Then by this definition right here, this is simply p2 times p1. And then by this definition right here, p2 is x1 squared plus x2 squared plus x3 squared, and so on. And p1 is x1 plus x2 plus x3, and so on. And so now what we're going to do is we're going to express our chromatic symmetric function as a sum of power sum symmetric functions. And so for this, what we need to do is we need to take a subset of edges. And once you have this subset of edges of your graph, then lambda s is going to be the partition determined by the connected components of your graph G respected to that subset S of edges. So let's have a look at an example. If this is our graph right here, then if we restrict it to the edge E2, we get this graph right here. And if we look at the size of the connected components, we get 2, 1, giving us 2, 1. And so with this in mind, the chromatic symmetric function of our graph in terms of power sums is as follows. What we're going to do is we're going to take a subset of edges, then we're going to make the partition determined by that, take that power sum along with an appropriate sign, and then we're going to add it all up. So let's do an example. So let's take our running example right here, our path on 3 vertices. So if we restrict ourselves to the edges E1 and E2, we get this graph right here. If we look at the size of the connected components, we get 3, giving us a P3. If we restrict ourselves to the edge E1, we get this graph right here. And looking at the size of the connected components, we get 2, 1, giving us P21. If we restrict ourselves to the edges just E2, we get this graph right here. And looking at the size of the connected components, we get 2, 1. And so that gives us another P21. And don't forget that appropriate sign. And then if we restrict ourselves to no edges, we get this graph right here. And then if we look at the size of the connected components, we get 1, 1, 1, giving us our P1, 1, 1. Our next basis is going to be that of the elementary symmetric functions. And now for this, what we're going to do is EI is going to be xj1, xj2 up to xji, where these indices right here are always going to be strictly increasing. And then for a partition lambda, E lambda is simply going to be E lambda 1 times E lambda 2, and so on. So for example, if I wanted to compute E21, then by this definition right here, this would be E2 times E1. And then by this definition right here, E2 is going to be the sum of, well, all monomials with 2 variables where their indices are increasing. So things like x1, x2, x1, x3, x2, x3, and so on. And then E1 is just going to be x1 plus x2 plus x3, and so on. And now, if we want to express our chromatic symmetric function as a sum of elementary symmetric functions, we have another really cool formula, but a little bit more intricate than the last one we saw. So if you want to write your chromatic symmetric function as a sum of elementary symmetric functions with coefficients C lambda, well, if you add up all of the coefficients C lambda, well, lambda is a partition with K parts, then what you get is the number of acyclic orientations with K sinks, where remember, an acyclic orientation is if you take your graph and you put directions on the edges, you get an acyclic orientation if you can't go round in a cycle. And remember, a sink is going to be a vertex where you have all of your directions coming inwards. So let's have a look at an example. So if we take our running example down here, and if we look at E3, which has 1 part, we need to look at the number of acyclic orientations with 1 sink, of which there's 1, 2, 3. So our coefficient is 3. Similarly, if I want to look at E21, which has 2 parts, then the number of acyclic orientations with 2 sinks is 1. So our coefficient is 1. And for our third basis that we're going to need to consider today, what we're going to need to do is we're going to need to go back to our partitions and we're going to need to make diagrams from them. And so a diagram of a partition is simply going to be the array of boxes with lambda I boxes in row I from the top. And then what we're going to do is just left justify them to make everything neat and tidy. So if I wanted to make the diagram of 3, 2, 2, 1, I'd have 3 boxes in my top row, then 2 in my second, 2 in my third, 1 in the end, and then I'm just going to left justify them all. And then what I'm going to do is I'm going to fill those boxes with numbers to give me a semi-standard Young tableau. And so a semi-standard Young tableau of shape lambda is going to be a filling of those boxes with the numbers 1, 2, 3, and so on. So the rows weakly increase as we read from left to right, and the columns strictly increase as we read from top to bottom. So let's have a look at this example right here. So notice here we've got 1, 1, 1. That row is weakly increasing because it's just staying at 1. Then we've got 2, 4, that's definitely increasing, 4, 5, also definitely increasing, and 6. And our columns are strictly increasing from top to bottom. We have 1, 2, 4, 6, 1, 4, 5, and 1. And then given a semi-standard Young tableau, you can associate a monomial to it. All you're going to do is you're going to take x1 to the number of 1s you can see, x2 to the number of 2s you can see, x3 to the number of 3s you can see, and so on. So if we go back to our example right here, we're going to get x1 cubed, x2, x4 squared, x5, and x6. And so at this point, we can now define our SCHUR functions. So the SCHUR function is just defined to be the following thing. What you're going to do is you're going to take all of your semi-standard Young tableau of shape lambda, you're going to make the monomial associated with it, and then you're going to add them all up. So let's do an example. So we wanted to compute the SCHUR function S21. Well, the first thing you would do is make all the semi-standard Young tableau of shape 2, 1, and here are all the ones that contain the numbers 1, 2, and 3. And then you're going to make the monomial corresponding to it. So from this one, I'll get x1 squared x2, giving me x1 squared x2. And then this one here is going to give me x1, x2, x3. This is also going to give me x1, x2, x3, thusly giving me 2 x1, x2, x3. And the formula for the chromatic symmetric function in terms of SCHUR functions is not so nice. So Wang and Wang actually have a formula, and what they did to get it was they ostensibly used formulas that were already known for the chromatic symmetric function and also transition matrices that are known for classical symmetric functions and combined them. And so now what we're going to do is we're going to move on to the next part of our talk, which involves E-positivity and SCHUR-positivity. So we say that a graph is E-positive if its chromatic symmetric function is a positive linear combination of elementary symmetric functions, and is SCHUR-positive if its chromatic symmetric function is a positive linear combination of SCHUR functions. So our running example we see is both E-positive, all of those coefficients are positive, and it's SCHUR-positive, all of those coefficients are positive. However, if we take this graph right here, then notice that it is neither E-positive, because look at that negative coefficient right there, nor is it SCHUR-positive, look at that negative coefficient right there. And in fact, K13, otherwise known as the claw, is the smallest graph that's not E-positive, and it's also the smallest graph that's not SCHUR-positive. Now, E-positivity and SCHUR-positivity are actually very closely linked because, well, if you want to write the elementary symmetric function as a sum of SCHUR functions, well, you can compute these coefficients right here combinatorially. And this is just the number of semi-standard Young tableau of shape mu filled with lambda 1 1s, lambda 2 2s, and so on. And then this index right here is the transpose of your partition mu, which is just you take mu and you flip it along the downward diagonal. So what do I mean by that? Well, I mean what you do is you take your diagram, you grab it along the main diagonal, and then you flip it. And that's the transpose. So take your shape, grab the main diagonal, and flip it. So let's do an example. If we want to compute E21, then what we're going to need to do is we're going to make all the semi-standard Young tableau that have 2 1s and 1 2. And here they are right here. Then what I'm going to do is I'm going to take this one, flip it along the main diagonal, which will give me a 2 1 and an S21. Then I'm going to take this one right here, flip it along the main diagonal, and that's going to give me 1 1 1, giving me an S111. And so notice that since we're counting something, all of these coefficients are going to be greater than or equal to 0. And so that means that if we have an E-positive function, it's also going to be a SCHUR-positive function. So why should we care about E-positivity and SCHUR-positivity? Well, If a function is E positive, then it's related to permutation representations. And as we just saw from the previous slide, if something's E positive, then it's SCHUR positive as well. And if something is SCHUR positive, then it arises as the Frobenius image of some representation of a symmetric group, and it also arises as the character of polynomial representation of a general linear group. And there is also the Stanley-Stembridge conjecture, and that's what we're going to look at next. So, Stanley and Stembridge, back in 1993, conjectured the following thing. Now, they put it in a different language, but we're going to give it in the language of chromatic symmetric functions. And they said, if an incomparability graph of a 3+1 free poset, if G is an incomparability graph for 3+1 free poset, then its chromatic symmetric function is E positive. So let's unpack that statement. In particular, what does it mean to be an incomparability graph of a 3+1 free poset? Well, if you've got a poset or partially ordered set, it has 3+1 if you've got 3 elements in a chain and then 1 element incomparable to it. And then if you want to make the incomparability graph, well, what you do is if 2 elements are incomparable in your poset, then you make them adjacent in your graph. So notice that if something is 3+1 free, then its incomparability graph is claw free, because here's our claw again. Now, this conjecture is still open. However, in 1996, Gasharov was able to prove the weaker result for SCHUR functions. He proved that if G is an incomparability graph of a 3+1 free poset, then its chromatic symmetric function is SCHUR positive. And so what we're going to do right now is we're just going to slightly rephrase that conjecture. So Guy Paquet, who many of you know, showed that it was enough to prove the conjecture for what's known as unit interval graphs. And so informally, how you can think of that is it's a connected intersection of complete graphs that have been laid out in a row. So what do I mean by that? Well, recall that the complete graph is going to be the graph on n vertices, if it's Kn, such that every pair of vertices is adjacent. And then what we're going to do is we're going to lay out our complete graphs, any formulation of them in a row, and then we're going to smush them together. So let's illustrate this with an example. So notice this thing right here is a unit interval graph because here's a K3, here is 1, 2, 3, 4, 5, a K5, and here is 1, 2, 3, 4, a K4, and notice how I've smushed them together. And so the Stanley-Stembridge conjecture in terms of this new language is as follows. If G is a connected intersection of complete graphs, then G is E positive. Now, while the conjecture is still open, we do have some special cases for which the conjecture has been proved to be true. So in 1993, Stanley and Stembridge actually managed to show that the result was true for 2 complete graphs intersecting. And in Stanley's original paper on the chromatic symmetric function, he was able to show that complete graphs K2 intersecting at vertices also satisfied the conjecture. And notice that this graph is better known as the path. In 2001, Gebhard and Sagan were able to prove that the conjecture was true for complete graphs only intersecting at a vertex. And then Samantha DAHLBERG in 2018 was able to show that complete graphs or triangles intersecting only at an edge also satisfied the conjecture. And then very recently, we were able to show some more cases. So this I did with my undergrad research student, Victor Wang, and my postdoc, Farid ALINIAEIFARD. And so for this, what we're going to do is we're going to redraw the complete graph first. So notice that you can draw the complete graph as follows, have all of your vertices in a line, and then add in the extra edges. And notice this is definitely the complete graph, because if you check, every single pair of vertices are adjacent. So by definition, this is the complete graph. So we were able to prove that we had E positivity for ice cream scoops. So what we're going to do is we're going to take the complete graph and we're going to melt edges away from either the right or the left, in this case, the right. So here we are, we've got all of our rightmost edges and we're going to melt them away, melt, melt. That's your ice cream scoop. And notice that this is an intersection of two complete graphs. What you can do is you can take all of the vertices underneath the cyan edge and all of the vertices underneath the magenta edge. So this is a new case of the Stanley-Stembridge conjecture that's been solved. We also have E positivity for snowy peaks. Now here what you're going to do is you're going to take the complete graph and you're going to melt away this top edge like that. And then what you're going to do is you're going to add dribbles from the right or left. In this case, I'm going to add it from the left. So here's my dribble, you add a vertex, and then you start adding in edges, dribble, dribble. And notice that this is an intersection of complete graphs, because notice you can take all of the vertices under the cyan edge, that's a complete graph, all of the vertices underneath the purple edge, that's a complete graph, and all of the vertices underneath the magenta edge, that's a complete graph. We also have E positivity for peaky snows. So now what we're going to do is we're going to take the complete graph and we're going to melt edges away from one of the sides, in this case, the right side. And then once we've melted away our edges, we're going to add just one dribble. Here it is, one dribble. So that's a peaky snow, and notice that this is also an intersection of complete graphs. You can take all of the vertices underneath the magenta edge, that's a complete graph. All of the vertices underneath the purple edge, that's a complete graph. And all of the vertices underneath the cyan edge, that's a complete graph. So the peaky snows are also E positive and are another new case that satisfies the Stanley-Stembridge conjecture. And in fact, we were also able to show that you can start actually connecting these graphs together to get bigger graphs that satisfy the Stanley-Stembridge conjecture. So if we have a connected intersection of graphs where you're connecting things at the rightmost and the leftmost vertices of any combination of ice cream scoops, snowy peaks, peaky snows, complete graphs, triangular ladders, then the resulting graph is E positive. So notice that this is an example right here. Here we've got a peaky snow, here we've got an ice cream scoop, and here we have a snowy peak. So we are guaranteed from what we've seen on the previous slides that this new graph here is E positive. So a natural question to ask is, well, how can we widen the conjecture? And so, well, you know, complete graphs have many, many edges. So what happens if we expand this out to as few edges as possible? Let's look at trees. So recall that a tree is a connected graph that contains no cycles. So here we have a tree, but this is not a tree because it's got a cycle right here. And so if we look at the number of vertices and the number of trees that are on those vertices, and then we look at the number that are E positive, we see there aren't very many. We know we're always going to have at least one because we know that the path is E positive. But are there any others? We don't really know in general. We just know there aren't very many of them. And so this was done by myself, Samantha DAHLBERG, who was my postdoc, and Adrian Shee, who was my undergrad research student, who's now a PhD student at the University of Toronto. So what did we discover? Well, we were able to prove that any tree with a vertex of degree at least the number of vertices taken to the log base 2 plus 1 is not E positive. So if we look at this tree right here, then we know it's not E positive because we have 6 vertices taken to the log base 2 is 2 and a bit, plus 1 is 3 and a bit, and we have a vertex of degree 4. Now we actually believe that something much stronger is true. We actually believe that any tree with a vertex of degree at least 4 is not E positive. And Kai Zheng, who's an undergrad at Princeton, was actually able to prove that any tree with a vertex of degree at least 6 is not E positive, which is completely amazing that he was able to make so much progress. But going back to the original conjecture, we know that if it's true, and in fact, we've actually been able to prove it independently, that this family of trees right here is not E positive because it has a vertex of degree 4. So how are we able to prove this? Well, what we did was we used an E positivity test of Wolfgang III, who was a PhD student of Richard Stanley. And what we did was, well, I'll give you the test in a minute, but we'll lay down some notation first. So we say that a graph has a connected partition of type lambda if we can find disjoint subsets of the vertices such that when you take the union of all of the subsets, you get back all of the vertices. And if you restrict the edges to a given subset, then you get lambda I vertices. So let's have a look at an example. So let's take this graph right here. Then, well, we know that it has a connected partition of type 4, because if we put all of the vertices into one subset, then we get 4 as the connected components. It also has a connected partition of type 3-1, because if we put these 3 vertices into one subset and this into another, they're all connected. And so we're going to get the connected partition of type 3-1. Similarly, if we have a connected partition of type 2-1-1, because if we put these 2 vertices into one subset, this one into another, and this one into another, they're all connected. So we have a connected partition of type 2-1-1. And if we put each of the vertices into its own subset, we get 1-1-1-1. But notice that we are missing a connected partition of type 2-2, because if we try to partition our vertices into 2 sets of 2, they're not connected. So we're missing a connected partition of this type. And so now we can come to our E positivity test. So we say that if a graph G is E positive, then G has a connected partition of every type. So that was Wolfgang's theorem. And so now if we take the contrapositive of that, we have that if G does not have a connected partition of some type, then G is not E positive. So we're guaranteed that our old friend the chlor, since it does not have a connected partition of type 2-2, as we saw on the previous slide, it is not E positive. And we can also have some results on the SCHUR-positivity of trees. And so in this case, we were able to show that if we have any tree with a vertex of degree, well, the ceiling of the number of vertices over 2, then you're guaranteed that it is not SCHUR-positive. So for example, this graph right here is not SCHUR-positive because we have 6 vertices, 6 over 2 is 3, and we have a vertex of degree 4. But this is not the end of the story. There are actually many open conjectures still in this area. So a number of them actually have to do with spiders, because spiders turn out to be the core type of graph in all of these studies. And once you can basically conclude things for spiders, you can conclude things for other trees as well. So what is a spider? Well, a spider is, well, what you're going to do is you're going to take a number of disjoint paths, and then you're going to join them together in a central vertex. So for example, if we wanted to make the spider 6, 2, 1, we'd take a path of length 1, 2, 3, 4, 5, 6 here, a spider of length 2 here, and then, a path of length 2 here, and a path of length 1 here. And then we're going to join those 3 paths up on a central vertex, and that's going to give us our spider. So now we can actually move on to some of the conjectures. So as we had from the earlier slide, we still believe that any tree with a vertex of degree 4 or 5 is not E-positive. We believe that the family of spiders where you've got a path of length 2 times 2m plus 1, a path of length 2m, and a path of length 1, all joined at a central vertex, is E-positive. And more generally, if you've got a path of length n times n factorial m plus 1, a path of length n factorial times m, and a path of length 1, all joined together at a central vertex, that's also E-positive. And we also believe that if a spider is E-positive, then so is its line graph. And remember, what's a line graph? Well, what you do is you take your graph, and then for each edge, you make a vertex, and then you join them up if those two edges meet at a vertex in your original graph. Okay, so widening the conjecture to trees was too much. So let's try shrinking it down to, well, another conjecture of Stanley's that dates from 1995. So Stanley said, we don't know of a graph which is not contractible to our claw K13, even regarding multiple edges of a contraction as a single edge, which is not E-positive. Well, after 25 years, we actually do. And so this is work with Samantha DAHLBERG, who you heard about earlier, Angel Foley, who's just down the road from you at Wilfrid Laurier, and myself. So before we actually resolve this problem, let's unpack this statement. So the statement involved the claw, otherwise known as K13. So what does it mean to contract the claw? Well, it means that shrinking the edges and identifying the vertices and removing multiple edges leaves you with the claw. And so Stanley's statement was saying the following thing. We don't know of a graph which is not contractible to the claw, which is not E-positive. So Stanley's statement is saying we don't know of anything that lies outside of this Venn diagram. Well, how are we going to tell rigorously if a graph is claw contractible free? Well, for this, we need to go back to the work of Brouwer and Veldman from 1987. And they proved that, well, a graph is claw contractible free if and only if deleting all sets of 3 non-adjacent or independent vertices gives disconnection. So notice that in these 4 graphs right here, if I delete the 3 non-adjacent or independent magenta vertices, I get disconnection. And in this case and this case, when I delete the set of 3 non-adjacent black vertices, I also get disconnection. So all of these graphs right here are claw contractible free. And if we compute their chromatic symmetric function, then notice they are not E-positive because we have a bunch of negative coefficients right here. And so therefore these lie outside Stanley's Venn diagram. And in fact, they are the smallest counterexample to Stanley's statement. Now, at this point, you might say, aha, but Steph, sometimes, things happen with small graphs on a small number of vertices, but maybe when we get a large number of vertices, everything is okay. But then I'd come back to you and I'd say, aha, but no, let me introduce you to the family of SALTIRE graphs. So the family of SALTIRE graphs is defined as follows. What we're going to do is we're going to have this configuration in the middle right here, and then a path with n vertices on the left and a path with n vertices on the right. So here is the SALTIRE graph 3, 3. And so, well, if we have a look at this, then it's claw contractible free because if you delete any 3 independent vertices, you're going to get disconnection. And if you look at its chromatic symmetric function, and you look at the coefficient of E and N in its chromatic symmetric function, then you get -n, n-1, n-2. But you might be saying, aha, but this SALTIRE graph, it's got an even number of vertices. Maybe things are okay with an odd number of vertices. But I would come back to you and I'd say, nope, sadly, that is not the case, because let me introduce you to the augmented SALTIRE graphs. So Here what I'm going to have is I'm going to have this configuration in the middle, which is like the one that we saw for the SALTIRE graphs, but it's been augmented by an extra edge. And then what we're going to have is we're going to have a path with n vertices on the left and a path with n or n plus 1 vertices on the right. This is really important. Then if this is the case, then in the same way for SALTIRE graphs, we have that these graphs are claw contractible free. And if you look at the coefficient of ENN or En plus 1n in its chromatic symmetric function, you get minus n, n minus 1, n minus 2. But at this point you might say, but Steph, remember you kept talking about things involving the claw. So maybe the graph needs to be claw-free, which means it does not contain the claw as an induced subgraph of your graph. So let's have a look at these two graphs right here. Notice that our SALTIRE graph is not claw-free because we can see a claw right here. But if I go to this graph right here, well, if I try and make a claw, well, I need to first of all find myself a vertex of degree 3. Here's one right here. And then if I try to make the claw, well, if I look at the 3 edges coming out of that, it doesn't make a claw because I've got a triangle right here. But that's not actually very rigorous. For the more rigorous result, we need something from Beinecker dating from 1970. And he showed that a graph is claw-free if there exists an edge partition, so partitioning of the edges, such that your partition gives complete graphs and every vertex is in at most 2 of those complete graphs. So we now know that this is claw-free because we can have the partition into the top triangle and the bottom triangle. Those are 2 copies of K3, and then just every other edge on its own. And those are copies of K2. And so with this in mind, we're now going to introduce the triangular tower graph. So what that's going to be made out of is going to be a top triangle, a bottom triangle, and then you're going to have a path with n vertices on the left, a path with n vertices in the middle, and a path with n vertices on the right. And so here is a 3-dimensional version of the triangular tower. You've got your triangle on the top, your triangle on the bottom, and then you've got your 3 paths. Then with this in mind, well, we know that the triangular towers are claw-free. We've just discussed that. They also turn out to be claw-contractible free because if you remove 3 independent vertices, you get disconnection. And if you look at the coefficient of ENNN in its chromatic symmetric function, then you get minus n, n minus 2, n minus 1 squared, n minus 2. But again, this is not the end of the story yet, because there seem to be other families out there that satisfy this. We just weren't able to actually prove concrete results about them. So one of them leads back to the graph we saw many slides ago, that hexagon with the crossbars, otherwise known as K33. And what you can do is you can just focus your attention on one edge and start throwing on multiples of 3 vertices. And if you do that, then the coefficient of e through to the n, we believe is minus 3 times 2 to the n. And we also believe that no graph exists that's connected, claw-contractible free, and claw-free and not e-positive with 10 or 11 vertices. What we believe is the first one you come across is your triangular tower 333, and then the next one you're going to come across is the triangular tower 444. Now, one thing you might wonder is why did Stanley not discover these things earlier on, back in 1995? And the reason for this, one of them, is that the computing power simply wasn't there. So a lot of these graphs that I've shown you have massive chromatic symmetric functions. So that was one reason. And another reason is even when you do find these graphs, then what you have is that they're incredibly scarce. So if you have graphs on 6 vertices, then only 4 out of 112 connected graphs are Claw contractible free and not E positive. Graphs on 7 vertices, only 7 out of 853 connected graphs are Claw contractible free and not E positive. And when you go to graphs on 8 vertices, then only 27 out of over 11,000 connected graphs are Claw contractible free and not E positive. And even when you find these graphs that are Claw contractible free and not E positive, those negative coefficients are extremely rare. So the 293 terms in the triangular tower 777, the only negative is where we said it would be in our theorem. The 564 terms in the triangular tower 888, the only negatives are where we said they would be in the theorem and one other place. And of the over 1,000 terms in the triangular tower 999, the only negatives are where we said they would be in the theorem and in one other place. So with that in mind, let's summarize what we've just been learning about. So remember, Stanley's statement said that he believed that nothing lay outside of this Venn diagram. However, we were able to show that actually there are infinite families of graphs that lie outside of this Venn diagram, either with an induced claw or without. And so therefore, the conclusion is that even though for 25 years, people have believed that the claw is really the crux to E-positivity, in general, E-positivity actually has nothing to do with the claw. So on that note, let me just say thank you very much.
Thank you so much, Steph. Let's give a round of applause. Feel free to unmute if you want. And does anyone have questions they want to ask? Feel free to unmute and go for it. I'll go ahead and start with one thing.
Yes, please do.
I'll start with a slightly perhaps obvious question. Did you check whether those graphs were SCHUR positive or not? I know that the other conjecture of Gasharov's is that it's claw-free graphs that are SCHUR positive. So since you have a family of graphs that are indeed claw-free, but are not E positive, it seems natural to check if they are also not SCHUR positive.
That's an excellent question, Logan. So yes, they are SCHUR positive. Mm-hmm. So yes, that's great. I'll definitely go and double check, but I seem to remember that was what we found. Yeah, that's a great question.
So what does E-positivity have to do with?
Sorry?
I think you froze briefly, Kevin. Could you repeat the question?
If E-positivity has nothing to do with the claw, what does it have to do with?
So in general, and this is the whole kind of like why the Stanley's temperature conjecture is really special, because it actually does seem to be the crux of that conjecture, but if you try and widen it slightly, everything falls apart. So E-positivity has everything to do with Stanley's temperature. Does that make sense? I think Kevin's frozen again. Nope. So was that
a good answer for you, Kevin? I think you froze again briefly.
Okay, wonderful, thank you. So yeah, there's something really special about unit interval graphs. I guess that's the ultimate punchline, that unit interval graphs have something very special about them with the E-positivity. And there may be other families, as we saw with the trees and things like that, that are not unit interval, but still E positive, but somehow there's something very special about that particular very large family of graphs. So yeah, great question. Thank you.
Any other questions? I might ask one more before we go. I asked you the same question, I think, the last time I saw you at a talk, but I still have the same question. In most of the coefficients that are negative in these graphs have lots of repeated numbers, like it's E777 or E44444, even with the claw it's E22. I know we've talked about whether there's something there to do with factoring or symmetry or something of the sort. Just wondering if there was any progress on that.
Not so far, not so far. There's, as you say, there's definitely something. I mean, all of the, yeah, it really jumps out at you, like all of these negative coefficients, they're all happening at rectangles, but it's, yeah, there doesn't seem to be any rhyme or reason that we've been able to see. So yeah, that would be really great if someone could actually make the connection, you know, like, because I mean, we all know rectangles, you know, they always have like nicer formulas and things. So you'd sort of think there'd be something we could leverage there, but yeah, still haven't found anything there. I'm still keeping my fingers crossed that someone will tell me why rectangles are so special in this case. So it's still a wonderful question. Thank you, Logan.
Same, looking forward to it.
Yeah.
If no one has any further questions, let's give Steph another warm round of applause.
Thank you. And thank you very much for inviting me. It was great to see you all.